Okay, let's go ahead and get started. Um, we'll see where we get to today. I have a bunch of things that sort of a grab bag before we get to, I think, one of the more interesting ways of looking at differential equations, which is the series solution. Um, but first, just as an overview, today we're going to kind of look at different ways of solving particular kinds of differential equations. And then probably get to series solution, at least an intro of that, and that'll bleed into next week. The main thing that you should have on your radar, of course, is that your first exam is on Monday. I'm still in the middle of writing it. It'll, as I said before, it'll be 4 questions. You can choose 3 of the 4. Open book, open notes, just can't use the internet apart from accessing the exam. That means no Wolfram or anything like that. You shouldn't need it, and anything that would even remotely resemble something like an integral table, something that you could find in ARFCN. It's one of the reasons why ARFCN's a good book. But the exam's really meant to be done in an hour. If you need to take more time, that's fine. I'd like to be able to post the solution and start grading it by 5 on Friday. So really try and do your best to get it done in an hour, but if you need to take a break or whatever, then do that. Are there any questions about the exam? Nope. Okay. Also, I have a couple of outstanding homeworks. As soon as I get those in, I'll post the solutions for the problem set. The only thing I'll say about the problem set, just in terms of trying to allay your fears, maybe, is that there was one problem in particular that was maybe a little more complicated than I meant it to be. So sorry. Or at least more opaque, which was the delta function, at least part C with the delta function. I'm not sure if anybody got all the way through that problem. I wouldn't be surprised if you didn't, because your textbook actually used, I wouldn't say the wrong identity, but not the identity I would have used. You can get to that identity from what they gave you, but it's a long, torturous road. So I'm not going to be worrying if you got part C, and I apologize if you spun your wheels on that. But basically, it was trying to look at essentially orthogonality and completeness for that expression, and for something like for a delta function that's x minus a, where a was equal to 0, essentially. But anyway, you'll see that in my solutions. Oh, did I see something?
It was just a joke, sorry.
Oh, okay. Yes, I noticed. Yes, sorry, I didn't have my chat window open. But thank you, Adrian. You are not the only person who said, and then a miracle happened. So anyway. So anyway, I think the rest of that homework was probably straightforward, I hope. If not, don't worry. The solutions will be up as soon as I get those last couple of homeworks in. And of course, you can talk to me during office hours or any other time, just ping me. All right, if there are no questions about the exam, let's get started. I want to just remind you of where we left off. Last time, I did some examples based on our general solution for differential equations. And what I've just rewritten, and you have this in your notes, are equations B20 and B21. And just want to be more explicit about how this is the homogeneous solution for the differential equation, and this is the particular solution of the differential equation that we looked at before with our P and Q functions. And in particular, because there was some confusion with some of my conversations with you, try not to get too confused with all the z's and the y's and all of that stuff. Those are dummy variables for the integration. And of course, we don't have to worry about Q up here when you have a homogeneous equation. Okay. So I mean, you have this in your notes, but I just wanted to bring that out because that was the topic of a couple of conversations. Before I get to series solutions and the Frobenius method, I want to consider, I think, three special cases. Some of which your book kind of goes over, and some of it does sort of buried in the homework. The first one is a special case if we consider the derivative of y, the first derivative of y, to be a function of y divided by x. Okay. So the question then is, if this is true, what can we do with first order? Again, remember, we're looking at first order ordinary differential equations. And this is going to set up something we're going to do with Bernoulli's equation and some other ways of attacking these things. What we're going to do is let z of x be equal to y of x divided by x. And the goal here, as with the Bernoulli equation and others, is to try and get things into a separable form, if that's at all possible. From this, we can write that y prime is equal to x times z prime plus z. And from that, we can get xz prime, just rewriting a little bit, plus z is equal to f of z. And then we can separate so that z prime is equal to f of z minus z over x. And then the integral of dz over f of z minus c is equal to the integral of dx over x, which of course is equal to the natural log of x plus the natural log of c, which of course we could just make any kind of constant. Okay. In other words, if we can start up here, if we can identify the derivative of y with respect to x as a functional form like this, we can change variables, solve for z, and then solve back for y. So just a completely artificial mathematical example. Let's suppose we have a differential equation that looks like this. xy times y prime is equal to y squared minus x squared. To get this into the form we want, we isolate y prime. So that's y prime is equal to y over x minus x over y. That's fortunate. Right, so now we have y prime. Let's see. Oh, sorry. Don't repeat myself. So now we have x times z prime plus z is equal to z minus 1 over z, recognizing that we have y over x and x over y. So that means we have z dz is equal to minus dx over x. So that gives us z squared is equal to some constant minus 2 times the natural log of x. Right? And then we solve for y, which is just y is equal to x times the square root of sine minus 2 log of x. And if we want to get any further than that, we need our boundary conditions. Right? So this is just a simple trick. If you can identify a differential equation like we have over here, right, that clearly depends on the ratio of x and y. It's not necessarily the most obvious or usual differential equation you run into, but you will occasionally. Now the next two are more you will see more often. First one you've seen already plenty of times, and I'll use that case to demonstrate how we go about this. And that's an ordinary differential equation with a constant coefficient. Okay, so our second special case for the day is ordinary differential equations with constant coefficients. Well, what do we mean by that? We mean that, and this could apply, in fact, generally does apply to nth order differential equations. The way that you would think about this is, for example, the nth derivative of y with respect to x plus, say, an we should have an a sub n out here, times a coefficient a times, or a sub n minus 1 times the n minus 1 derivative with respect to x of y, plus on down the line to dy dx plus a naught times y, where all of these are constants, and this in general can be equal to a function f of x. So the question then is, how do we go about solving this? And the easiest thing to consider here is the homogeneous case. So we consider y sub h of x, right? That means that f of x is equal to 0. Then we can posit that y sub h of x is equal to e to the mx, where m is actually going to be the roots of an indicial equation. Well, not really an indicial equation, a coefficient equation. So if we're going to assume a solution like this, we're also assuming that m to the n plus a sub n minus 1 times m to the n minus 1 plus, and so on, to a1 times m plus a naught is equal to 0. We're also assuming that a sub n is equal to 1, which we can easily do. We can just take the first constant and divide it out so that we just have y, the highest order derivative of y, isolated. Let's see, 6. All right, so these are the two conditions. Well, in fact, C.5 is the solution. C.6 is the condition on those m's. What you should realize is those little m's are the roots to this equation. So the simplest thing that we can think of here, is let's look at m d squared y dt squared is equal to minus ky, right? So simple harmonic motion with the spring. That means that we can write this as, say, y double dot plus a naught y is equal to 0, with a naught equal to k over m. So far, so good. That means, according to C.5, right, we have to look at all of those m's. What our homogeneous solution, and this time with respect to time, is equal to some constant C1 times e to the m1t plus C2 times e to the m2t. And our root equation is m squared plus a naught is equal to 0. That means that m1 and m2 are the roots of m squared plus a naught is equal to 0. Okay. This is a lot of work to solve a very simple problem, but if you imagine this being, say, a third order ordinary differential equation that looks like this, you can use this to find the roots for that solution. What you find, of course, is that m12 is equal to plus or minus I omega, which is equal to plus or minus I times the square root of m, right? And so we get what we normally would expect, which is y of t is equal to c1 times e to the I omega t plus c2 times e to the minus I omega t. In other words, we reproduce simple harmonic motion. But the idea with this is that if you have an ordinary differential equation with more terms than this, you could use this method. Okay. Okay, how are we doing? All right. The last special case before we start moving in the direction of series solutions is the Bernoulli equation. How many people have seen the Bernoulli equation? Okay, yeah, maybe, yeah. In the language that we have been using in this class, the class of equations we'd write as, again, this is a first order equation, y prime plus p times y is equal to q times y to the n. Okay, so we recognize this as a class of ordinary first order differential equations. And we'll see that it has actually a pretty immediate application. But you have to be careful. You have to sometimes you have to change your second order equation into a first order equation. For now, let's let z be equal to y to the 1 minus n. And we're doing this, as always, because we happen to know what the answer is going to be ahead of time. So, well, or you do if you've run into it before. So z prime is equal to 1 minus n times y to the minus n times y prime. And 1 minus n times y to the minus n times y prime plus 1 minus n p times y to the 1 minus n is equal to 1 minus n q. And so now we have z prime plus 1 minus n p z is equal to 1 minus n q. Now, the reason why we did this is now this is essentially our p, and this is our q from B point 20 and 21, right? So the whole point of something like this manipulation, in fact, a lot of manipulations with these first order differential equations that look bizarre, is to try and get it into the form, whether it's homogeneous or particular, of B20 and B21, okay? Now I have an example once you're in a position to do that. And it's actually an interesting example in that it seems like it's simple Well, it seems like it's simple and complex at the same time. Let me put it that way. So I don't know if that makes sense. Let's look at this equation. I got a couple of examples, but I think this one will work best. 4y double dot plus or minus 2y dot squared plus y is equal to 0. All right. Clear as mud. This is awesome. What might this look like? What might this represent? In other words, if you think about this as a differential equation that describes a physical system, what might this physical system be?
Would the y dot term be like a damping thing?
Yeah, exactly. So what we've got here is essentially, we've got our acceleration term. We've got now the plus or minus v squared would be a damping term that might depend on which direction. You might have this might describe a spring, for example, in a viscous medium or a dash pot attached to a dash pot, my favorite, dash pots, that retards the motion in either direction, either going down or coming up. And then if we throw this on the other side, right, we get our harmonic motion. In other words, if instead of 2 we have 0 here, right, we should just get simple harmonic motion. Right, so we could write this in terms of constants. I want to do this in terms of actual numbers just to get to where we need to go. So this is essentially a harmonic oscillator with v squared dissipation. Okay. But it's kind of complicated because the dissipation or the damping could go in different directions depending on how we start. All right. So what we want to do here is let's start changing some of these variables or identifying some of these variables. We'll let dy dt be equal to little p, and d squared y dt squared is going to be equal to little p dp dy. We're just chain ruling it out. And I realized after I started writing this last night that I'm using lots of P's. I apologize. You're physicists, you're used to us using the same letter over and over again. I'll make it clear when I use a big P. But I'm sorry. I know that's maybe confusing. All right, so we can rewrite this equation up here as our goal. So now we have 4 little p dp dy plus or minus 2 times little p squared plus y is equal to 0. Okay, so far so good. Now we can write dp dy plus or minus 1/2 little p is equal to minus 1/4 y little p to the minus 1. Okay, now we did all this so that we could get this not only into the Bernoulli equation form, but also to identify the pieces of it, right? So we have essentially our y prime piece here. We have over here our capital P. And we have over here our capital Q. And we've identified our value of n in the Bernoulli equation. Question remains then, how do we go about solving this? Well, just like the last couple of cases, we're going to make some further substitutions. So we're going to let z, in this case, be equal to p squared. That means that dz dy is equal to 2p dpy, and dz dy plus or minus z is equal to minus 1/2 y. Why did we want to do it this way? What's our end game here? What should be always be our end game if we are dealing with ordinary differential equations, first order ordinary differential equations? What equations are we headed towards?
B20 and 21.
Right. So we have gone, let me scoop this in. We've gone from here to here to here. Sorry about that. So that we can get into either B20 or B21. Those are solutions to first order ordinary differential equations if we can identify those capital P's and capital Q's. So given that we've just written it this way, we can write that the solution to this equation is z times plus or minus y is equal to minus 1/2 times the integral on y of y prime e to the plus or minus y prime dy prime. This is just following the same thing that we did yesterday or Monday. And so that equals minus 1/2 e to the plus y times plus y minus 1 plus a constant. And if we expand that out, that's equal to minus 1/2 times plus or minus y minus 1 plus c, I have this right. Yeah, e to the minus or plus y. Yep. So that means if we solve for z, we get 1/2 y plus 1 plus c e to the y. Now here, we're assuming, in this case, that dy dt is equal to 0 and y going down is positive. That's why we're taking this positive root. If we don't, we're kind of stuck back up here, or we're stuck with plus or minuses. But if in this particular case, where we're taking the positive case, where things are basically the spring is moving down and measuring things positively down, we get this for our solution. And we have to realize that z is equal to dy dt squared, right? So ultimately, this gives us at least y prime, and then maybe y of t. It depends on initial conditions. It depends on the form of the function, whether we can go any further. But double star is basically where we're headed. We're trying to essentially describe the velocity of something that's moving in this viscous medium with this kind of dissipation. And that's governed by Bernoulli's equation, which is something that you've seen, but seen in different contexts. So the point of all of this was that I wanted to go through at least 3 different special cases apart from the general solution for first order ordinary differential equations. All of them try and get back to B20 and B21. And you'll have some Most of the homework is on the first part of basically the lecture from Monday. Some of this stuff we'll come back to later on in class. So I'll stop here if you have any questions you need to stretch.
I have a question about the second special case before the Bernoulli equation.
Sure.
In the example, there was a capital M and a lowercase m, and I kind of got lost of which was which. Particularly the m squared plus a naught equals 0. Is that a lowercase m?
That's a lowercase m, sorry.
Okay. Okay.
Thank you. Again, this I should, yeah. I tried to move over to omega to avoid that confusion, and I forgot. Sorry, but yeah. Okay, are we ready? Okay, I'm excited. You can tell. One of, I think, the coolest things about solving differential equations, or one of the coolest methods for solving differential equations, are series solutions. It's one of the reasons why, one of the many reasons why we started down this road in the first place in the first week. Even though this is on the syllabus for next week, I do want to take my time developing it, and I knew it would probably take more than 2 classes, especially when we debrief after the midterm. So if you haven't read about that, this is fine. This is mostly setup. But the idea is that for a well enough behaved equation, we can identify, hopefully, at least one solution to a second order ordinary differential equation that can be written in terms of a power series. And then our goal is to find what are the coefficients for that power series. And that'll lead to things like recursion relations. So things that you've seen, whether or not you've seen where they've come from, Bessel's equations, Legendre equations, Chebyshev polynomials, all of those things come from assuming a power series solutions and then trying to match what those coefficients are and seeing if there's a repeating pattern. Maybe all the odd values are 0. Maybe all the even values depend on 2 steps before. Okay, so the first thing is to set up the problem and consider singular points. So we'll start with some definitions. We'll consider, in our usual way of writing a differential equation, y double prime plus a function p purely of x times y prime times a function q of x times y is equal to 0. We worry, or we need to be concerned about singular points if p of x or q of x diverges as x approaches some point x naught. If it does, then x naught is what we call a singular point. Which seems kind of obvious, I guess. We can divide these up, as we did with complex analysis, as regular, that is non-essential, and irregular, that is essential singularities. So regular is non-essential. Singular point would be something like, if we could take x minus x naught and multiply it by p of x, and that remains finite, for example, or x minus x naught squared times, say, q of x, and that remains finite. That's what we would consider a non-essential or regular singular point, something that we can work with. An irregular or essential singular point is the opposite of that. So, e.g., x minus x naught p of x still diverges. You can't get rid of it. Okay, 1 over log of x, say, x around x equals 0. Something like that. So, for example, let's check in with our friend Bessel. So Bessel's equation. So Bessel's equation is a bit like, and we've seen things like this with Legendre's equation in the first week of class. Bessel's equation is a second order ordinary differential equation, right, with indices and an apparently, well, no closed solution. And we'll see what that means in a minute. So essentially it's a generating function for the Bessel function. So x squared y double prime plus x y prime plus x squared minus n squared y is equal to 0 is our Bessel equation. Solution to which gives us the Bessel functions, or at least one kind of Bessel functions. In order to find, so what's our P? For this equation?
1 over x.
Yeah, 1 over x. So, and is usually the case with these equations, we want to clear out the highest order term so that there's nothing multiplying by it, right? So in this case, we divide everything by x squared. P of x is equal to 1 over x. Q of x is equal to 1 minus n squared over x squared. All of this means that x equals 0 is a regular singular point or a non-essential singular point. If we look at the case where x goes to infinity and we let z be equal to 1 over x, then we can look at the case 2z minus p of z minus z to the minus 1 over z squared and q of z minus 1 over z to the 4th. This diverges slower than 1 over z. This goes as 1 over z squared. That is, x at x equals infinity, we have a regular single point. That is, as z goes to 0, x goes to infinity. 3. Okay. So why are we doing this? We'll state without proving Fuchs's theorem, which makes this all possible. At least one power series solution or substitution is possible if the point of expansion is either an ordinary point, that is, doesn't have a singularity at all, or a regular singular point. Right, so that's kind of the only limitation that we have, is if we look at a function and we know that there are no essential singularities, we can find at least one series substitution. That is, we can substitute y of x as a sum of x to the n, and then by judicious matching of coefficients, find a solution, at least around that point.
Professor Pickett,
Yeah,
what's the first word on the third line of Fuchs' theorem?
possible.
Possible, sorry.
Sorry. Yeah, that's way more messy than usual. Sorry. So the basic idea is if you're dealing, I mean, in a sense, if you're dealing with poles, simple poles, if you were to look at complex series, you're fine. You get to higher order or worse, then you're not fine, at least for expanding a solution around that point. All right. So, substitution, solution. How do we proceed? All right. So let's consider the general case. So the general case is going to be linear second order ODE. And we can consider homogeneous and non-homogeneous cases too. For the homogeneous case, we're looking at, again, y double prime plus p of x, y prime plus q of x, y is equal to 0. We're going to assume if this is a second order differential equation, then there are two linearly independent solutions, right? So we assume two linearly independent, which is something that if we don't say it explicitly, we've certainly had a lot of experience with, namely y of x is equal to c1 y1 of x plus c2 y2 of x. Right. For the non-homogeneous case.
Wait, I have a question.
Sure.
What kind of solutions are we assuming?
Linearly independent solutions.
Okay. Thanks.
Right. So, and we'll look at basically the procedure that we're going to be following is we're going to assume one of those solutions is a series solution, a power series solution. Find that one, and then we can test using something called the Wronskian to find the other, right? Or to find, at least test that something is linearly independent, right? And the easiest example of that would be in this case for like a harmonic oscillator, sines versus cosines, right? Okay. All right, so the non-homogeneous case. Where f of x is our source term. Then we have y of x is equal to essentially everything we have here, plus what? What do we need to add? So we've seen this before. If we know we have a homogeneous solution, if we have a homogeneous equation or a situation that is, there's no source term, but then we add a source term. So we've done this with forced harmonic oscillators. What's our step once we put in a forcing function? I'll get you started.
exponential term.
Well, it would be an exponential term depending on the what the forcing function might be, right? We have to make a guess, but just in general, what are we adding here? What do we call this term? The particular solution, right? Depending on the function, we might add, say, a linear term or an exponential or another oscillatory term, right? And then try and match the initial conditions and match the, by assuming a solution, we're trying to show that it is the solution, sort of a uniqueness theorem, right? But when our general program of solving differential equations in all of your classes in physics has been generally to start with an homogeneous equation and then add a forcing term or a source term. And then the solution to that is take what you already did with the homogeneous equation and add some guess to how that's modified, right? And often that's a constant term, or often that's similar to what the forcing function looks like or the source term looks like. Okay. All right. So, but let's make life simple for us. We're going to assume a solution now. And we're going to consider the homogeneous case and positive powers, right? One of the things that we talked about and one of the reasons why we went down this road with complex series, right, is what's the difference between a complex power series and a real power series? Like the most general difference. In fact, you could tell it to somebody who didn't know anything about complex series, right? Think about the difference between a Laurent series and a Taylor series. What's the difference?
Negative ends.
Right. So we're assuming that the powers are positive, so our sum is just going to be over positive values of n, right? So we're going to assume y of x is equal to a naught plus a1 x plus a2 x squared plus a3 x cubed plus and so on a sub n x to the n 6, or the sum from n equals 0 to infinity of a sub n x to the n. So that's it. I mean, that's essentially all we need to do. We need to go back up to our original equation and consider what this looks like. In order to do that, right, we need to know what these derivatives look like, right? So for example, y double prime of x is going to be equal to the sum from n equals 2 to infinity of n times a sub n x to the n minus 2, if we block out those two terms that disappear after two derivatives, right? And that is equal to the sum of n equals 1 to infinity of n a sub n x to the n minus 1 if we just change the indices. These are d.7 and 8. Okay. And we can do the same thing for y prime. So what do we do? the method is, at least on paper, straightforward. Its execution can be really complicated, the mess of algebra, but it comes down to, and this has been the goal from the very first day of class, if you can change any calculus, whether it's differential or integral calculus, into algebra, do it. So this is going to change essentially the differential equation into an algebraic problem. So the method is to substitute D.6, 7, and 8 into D.1, and the tricky part, solve for the coefficients. So if you're lucky, we could solve for something that terminates. More likely than not, the series is not going to terminate. So let's look at, we have time for a simple example. Let's look at y prime equals 2xy. Now, that's not a difficult differential equation to solve, but it's a good thing to practice with this method. So we know that y prime, we know what y is. It's just the power series, right? Y prime is equal to a1 plus 2a2x plus 3a3x squared plus 4a4x cubed plus 5a5x to the fourth, and so on. 2xy is going to be 2 times x times that original series, namely, I'm going to write this suggestively as 2a naught x plus 2a1 x squared plus 2a2 x cubed plus 2a3 x to the fourth. And the reason why I did this, right, is I shifted things over because the way that we solve this is to identify the coefficients in front of the similar powers of x. So from this, right, what does a1 have to be equal to?
Zero.
Yep. So a1 is equal to 0. Remember, what we're saying with this equation, this means that this series is equal to that series. So we have to go term by term. All right, what about a2? What can we say about a2?
Equal to a naught.
Yeah, it's equal to a naught. We can't say anything yet about what its actual value is, but it has to be the same thing as a naught. How about a3?
2/3 A1.
So it's 2/3 a1, exactly, which is equal to 0, right? And then we can keep going down the line. A4 is equal to 1/2 a2, which is equal to 1/2 a naught. A5 is equal to 2/5 a3, A3, which is equal to 2/5 times 2/3, A1, which is equal to 0, and so on. Or we get that n times a sub n is equal to 2 times a sub n minus 2. In other words, a sub n is equal to 0 if n is odd, and 2 over n times a sub n minus 2 if n is even. Good. Now this, we're fine with what we're doing here. The trick with series solutions is to try and make this look like, if we can, a closed form. So what we want to do is look at our solution and see if we recognize it as an expansion that we've already dealt with, right? So given this, we'll let n be equal to 2m. We'll just reindex everything. And a sub 2m is going to be equal to 2 over 2m times a sub 2m minus 2. And that's equal to 1 over m times a sub 2m minus 2. And that's equal to 1 over m times m minus 1, a sub 2m minus 4. And we can keep going until we get to m factorial a naught. In other words, we can write y now in terms of this a naught as a naught. And we could have started this way from our original solution, but we're trying to get this into a different form. A naught plus a naught x squared plus 1 over 2 factorial a naught x to the 4th plus 1 over m factorial a naught x to the 2m. All right, so that means that y of x, our solution, our one solution, because again, at least with this case, we have no singularities, excuse me, is the sum from m equals 0 to infinity of x to the 2m over m factorial. Oops, sorry. There's an a naught in here. Y of x is equal to a naught, some constant. So what is that? Equal to some constant times what?
E to the x squared.
Right, e to the x squared. And that's it. I mean, that is the general idea, is that if you don't have any essential singularities, you can expand the function. You could substitute a power series into your differential equation. And then from that, write out what y is in terms of a power series. And if you're lucky, it turns out to be something that you recognize as a closed function. If not, you're left with a sum, and it could be, and there will be cases where you're just left with a sum that isn't resolved as a recognizable function. That's fine, especially if, say, x goes to 0 and you can approximate the solution to a differential equation with just a few terms. Okay, so this is an incredibly powerful way of solving ordinary differential equations. But the really important point here is, one, Fuchs's theorem, right? And two, we've only found one solution, which means that there's another lying out there somewhere, at least for second order. And the other thing that I would suggest, and we're running out of time, is that when you do these problems, do exactly what I did, which is line up the powers so that you can identify the coefficients in front of the like terms, the like powers of x. And then and it may be that you end up with what we call indicial equations. And I think this is in the homework. If not, I'll do it as an example. The Legendre equation is like that. So the Legendre equation, which you've seen before, looks like this: 1 minus x squared times y double prime minus 2xy prime plus n times n plus 1 times y is equal to 0. This is, again, is something that if you assume y is equal to a naught times x to the n, or sorry, an x to the n, you can go term by term, divide out one, you would divide out this term, and then you would find the expression for y double prime, the expression for y prime, and the expression for y, and see if you can find a relationship between, say, odd and even values. See if you can get a recursion relation for those solutions, for those coefficients. Okay. All right, I'm a little bit over, so I apologize. Before I go, obviously, are there any questions, but especially, are there any questions or concerns about the exam? No? Okay. Go ahead. Yes.
So again, so the exam will be at 10 a.m. until, and it will be accessible to hand it in until 5 p.m.
Right. So I need to finish writing it, and then I'm just going to make it available, turn it visible at 10 o'clock on Friday, Central Time. And then you have until 5, essentially. It's very purposely designed to be done in the hour that you would normally have, sort of a Lawrence hour. So, an hour and 20 minutes. Actually, I'm trying to reduce it so it fits in an hour. Yeah. And then get it to me by 5. 5 is when I'm going to post the solutions. Okay. And again, 4 questions. I will say, though there are 4 questions, 2 of them are going to be on complex analysis. So you can, if complex analysis is your thing, then do 2 complex analysis problems. If it isn't, then do the one that you can do better. Okay. And I'm going to just grade the first 3 that you send me. So please don't send 4 partial and have me try and figure out which ones are the ones that you want me to grade. I'm just going to grade 1, 2, 3 and stop reading after the 4th one. Okay. All right. Look at the practice midterm and ping me if you got any questions. Okay. Solutions for homework will be up hopefully shortly. All right. Bye, guys. Be safe. Be well. Good luck. You got this.
Bye, Meg. Bye, Willa.
Bye.
Bye, Adrian.
Good night, Jim Bob. Nobody knows what the Waltons are anymore.